When the sun goes down each day, we know it has to rise again tomorrow. We know the grass is green, the sky is blue, and that it's true that after winter, spring must follow. We claim to know the workings of the world and of ourselves, but what it really means to know, we've learned that nobody can tell. Or at least that it's very difficult. Because what even is knowing? How do we know if we know something? Or whether there even is an objective reality to know anything about. Philosophy, which is the art of thinking about stuff, has a whole field dedicated to only that. Epistemology, the theory of knowledge, or the stuff we think we know about knowing about the stuff we think about. No, wait. Historically, we've learned to rely on patterns of cause and effect, on cycles, or at least on correlation, to base our actions off of. It's been beneficial for our survival to try and predict what's going to happen and prepare for it. So our brains are still today deeply wired for this kind of behavior. But patterns can stop or change. Our senses can deceive us. Our memories can fail. So what can we actually trust to be true? Well, Descartes, for example, said you can't ever be sure if something is true, that it's possible to doubt everything. With one clear exception, because if there is doubt being cast onto something, there must be a mind casting that doubt. So that's where the I think, therefore I am conclusion comes from. Basically, all you can ever be sure of is your own existence. But that's one approach, and there's plenty of other thinkers with wildly varying points of view relating to how we obtain knowledge, what parts of it we can trust, and so on. And as a scientist, a person whose job is to find out more about the world, I'm interested in the approach used by science to define truth. So how does humanity's most successful knowledge acquisition endeavor separate what's real from what's not? And how useful is that for any given person's day-to-day life? In modern science, when there's some phenomenon that needs investigating, we employ some variation of what's called the scientific method. It's not perfect, of course, nothing ever is. There's a lot of biases in science, and that's a whole other discussion, but it has been developed over time to try and minimize the influence of things like existing assumptions and personal opinions or preferences of the ones carrying out the method. And depending on the type of research, the details change a little, but the basic structure of the method is as follows. 1. Start with an observation about something, or with a question you want to know the answer to. 2. Go gather information about your question or observation, be it finding more instances of the same phenomenon or looking for existing material on the topic. And that's one of the great things about science, the community. Because ideally, someone else's previous inquiries or research is published and accessible so that it can help whoever might want to know about it too. 3. Formulate a hypothesis, meaning try to explain why this thing you observed happens. What's the answer to your question? What's the underlying pattern governing this system? 4, and that's the big one, perform experiments to test your hypothesis. For example, if you think there's one specific aspect of a system that's causing something to happen, try to change only that part and observe the results. Or try to change all other parts of the system to see if nothing happens, if the results stay the same. That's also good. And the important thing in this part is that your experiments are well documented and reproducible, so that if anyone else wants to check them by themselves, they're always able to recreate every part of what you did. And finally 5, analyze and interpret what the results from the experiments might mean, and whether they make sense with your hypothesis or not. This is by no means a formal description of how stuff works or how it should work, but it outlines the general idea. And from there, usually the results are reviewed by others with experience in the field, the research is published, and so on. So you observe something, make a prediction on how it works, and then keep testing it to see if the explanation makes sense. If you think about it, it's similar to what we intuitively do as we go through life, learning how to solve our little problems and trying to improve on how we deal with things. I made a video about that too. But did you notice that we never actually get to the truth? Because if you make a hypothesis and it doesn't match with the experiment, then yeah, you know it's wrong. But if it does match, does it mean it is the correct hypothesis? Did you get your explanation right? Is your model true? Well, let me tell you a story about how we understand gravity. Isaac Newton had many great ideas, and one of them was that mass attracts mass. More specifically that the force between two bodies was proportional to how much mass they had and how close to each other they were. That hypothesis matched experiments, a wide range of them, from apples falling from their trees, to people tripping down the stairs, to how the solar system works, the orbits of planets and moons and stars. So that was a good model, and it still is for most users, but eventually we found some experiments that it doesn't predict correctly. Historically, it's been the orbit of Mercury, which has been observed to behave a little differently from what Newton's theory predicts, and also the fact that the path of light is bent by gravity, which seems to contradict that it's an interaction only between things with mass. These cases and others were later solved by general relativity, Einstein's theory of gravity, which not only works with all previous cases, so basically it reduces to the old theory, but it also makes it more complete, more general as the name says, and describes more phenomena related to gravity. So, was Newton wrong? Was he right before we figured out he was wrong? And is general relativity, in the way we understand it today, the true nature of gravity? Well, no. Because that's not what science does. It's a search for knowledge, sure, and it's great at eliminating the wrong hypotheses, but it never arrives at the truth. At least we can never say for sure it arrives at the truth, because even if a hypothesis matches with all experiments we've ever done with it, who's to say that the next one isn't going to break it and require an updated model? So, was Descartes right? That there's nothing we can ever be sure of? In my view, it's less about that and more about that the models we build, the ideas we have about how the world works, they get more refined with time, be it in science, with more research, more experiments, or in day-to-day life, with growing and experiencing more things and making mistakes and learning from others, and that's the best we can do. And even if we never arrive at something we can call an absolute truth, even if the answer is no, we can't actually know anything, we'll stay curious anyway. We'll keep looking, because we enjoy the process, not just the outcome. The road, not just the destination. Living in the universe, not just knowing about it. So we'll keep thinking, we'll keep trying to know, and we'll keep sharing the stuff we think we know about knowing about stuff we think about.